In the name of God. Hello, dear students. My name is Masoud. We are in Ferxwaz site. We have an application for Ferxwaz. You can download it on internet to, let's say, follow our lectures. I'm a physics teacher, and I want to explain the curriculum of physics, grade 10 for you. Let's get started. This is the, and I want to tell you before I go to the first chapter, I want to tell you the contents of this chapter. This chapter consists of three sections. The section 1, of course, by the name of God, we will start our subject. Section 1 talks about physics in general. What is physics? Section 2 talks about measurements in experiment. Section 3, let's say, talks about language of physics. Let's dive into the section 1. What is physics? Of course, this section talks about the physics in general, and especially it focuses on some theories about the falling objects. In general, it talks about a comparison between the Galileo's thought and Aristotle's thought about the falling objects. And another thing that this chapter focuses on is the scientific method and some other, let's say, some other things. Let's dive into the first subject. We want to explain, let's say, the first thing, the first section, and I told you it talks about the physics in general. What is physics? Of course, let's say I prepared some definitions for you of physics. Some of them are classical definitions. Some of them are new definitions. I chose 3 definitions for physics. Definition of physics. What's the physics in general? We want to, let's say, define physics. It's the knowledge that describes natural phenomena. By the way, this definition is definition for Aristotle. Aristotle, let's say, defined physics as this: is a knowledge that describes natural phenomena. And physics, the word physics, let me add this note for you. The word physics is not an English word. It's a Greek word. It means nature. It talks about the nature. So physics in Greek means nature, right? The second definition for physics is says that the second definition that it's the knowledge of matter and energy. It's the knowledge of matter and energy. Number 3, it's the knowledge of force and matter, and interaction between force and matter. Right? They are definitions for physics in general. The first one, it's very old definition, but the other 2 definitions are more modern than the first one. Actually, in our daily life, we are surrounded by physical phenomena. Whenever you, for example, blink your eyes, whenever you move your hand, whenever you say something, whenever a teacher presents a lecture, and right now I'm presenting a lecture for you, I use the principles of physics. I use, let's say, some principles that belongs to physics, right? These principles belong to physics, and your book, this curriculum, focuses on 7, let's say 7 area or 7 topics in physics. You can say area of physics or topics of physics, it doesn't matter. So firstly, I want to explain this one, topics of physics. Let's name them one by one, topics or areas of physics. The first one, mechanics or classical mechanics. You can say classical mechanics. The second one, optics. Actually, mechanics talks about the motion, and I'll explain it for you. Motion in general belongs to mechanics. Optics, anything that's related to our vision is optics. It belongs to optics. Number 3, thermodynamic. Thermodynamic, anything related to let's say, heat and thermal energy, it's, let's say, thermodynamic. It belongs to thermodynamics. Number 4, vibration and wave phenomena. Vibration and wave phenomena, like what? Like, for example, pendulum. I have a pendulum here. For example, this is a pendulum. Whenever you, let's say, move it back and forth, it vibrates. So it's a repetitive motion and belongs to vibration and wave phenomena. And another thing, number 5, electromagnetism. Electromagnetism. It's a relationship between electricity and magnetism in general. Electromagnetism. Relativity. The 6th one is the relativity, and I can say modern physics starts from here. Relativity theory of Einstein. Einstein, let's say, published it in 1905. Let's say this is called relativity theory. Actually, Einstein, by this theory, contradicts the idea of, let's say, idea of Newton. Newton said that, let's say, time is absolute, but in relativity theory, Einstein, let's say, opposed against this idea, and he said, time is relative. Time is not absolute; it's relative. And the last one, and I want to explain it for you, I want to name it for you, quantum theory. Quantum theory, let's say, proposed by Max Planck in 1900. At the beginning of the 20th century, this, let's say, this theory was born by, let's say, Max Planck. They are areas of physics in general. Let's say, I included the table here. The table, let's say, focuses on and on each area, and for each area we have a subject, and we have some examples about each subject. For example, the first one, mechanics, and I told you mechanics, or you can say classical mechanic or Newtonian mechanic. This is mechanics, subject of mechanics. What are the subjects that, let's say, belong to, let's say, mechanics? Motion and its causes. This is the first one. Any kind of motion belongs to mechanics. And I told you, whenever you catch a ball, whenever you take a step, whenever you blink your eyes, whenever you move your hand, they are examples of mechanics in general, right? Interaction between the objects and their subject. Interaction, how do they interact with one another? How do, for example, two players, how do two balls collide with one another? This is subject. These are subjects of mechanics in general. Example, falling objects. It's not failing, actually, it's falling objects. Falling objects like, for example, free fall objects. Whenever you, for example, throw this ball, whenever you throw it, this ball becomes falling objects, right? Friction. What's the mean friction? Actually, whenever you rub your hands against one another, this is called friction. And because friction, let's say, is due to motion, that's why it's an example of, let's say, mechanic. Weight. We have another example for the mechanic. We have weight. Well, what's weight? Weight means the gravitational force of Earth, let's say, because we live on Earth. Gravitational force of Earth on any object. This is called weight. So spinning objects. A spinning object like, for example, this ball. This ball spins about itself, right? This spins about itself. So I can say Earth spins about its axis. They are, let's say, examples of motion and its causes that belong to mechanics, right? Let's move on to another branch of physics or another area, thermodynamics. Thermodynamics, let's say, is driven from the word thermal. whenever you hear the word thermodynamic, think about the thermal energy. Thermal energy, so anything that related to heat and cold, let's say, I can say it belongs to thermodynamics. Subject of thermodynamic, heat and temperature. Heat and temperature belongs to the thermodynamic. These are subject of thermodynamics. Let's take a look at the examples of, let's say, heat and temperature. Melting and freezing processes. Melting means change of a state from what? From solid to liquid. Freezing process, change of a state from liquid to solid. Whenever you put a glass of water within the refrigerator, it freezes. It changes its state from liquid to solid. This is called freezing. And engines in general, motors of any machine, let's say, this is, for example, thermal motor or thermal engine. That belongs to thermodynamics. Refrigerator has a motor, yeah? Whenever you touch the motor or engine of refrigerator, you feel hot, yeah? The motor is very hot. It gets hot, actually. That's why refrigerators, let's say, belong to thermodynamics. Keep in mind that any change in temperature, whether the change is increasing the temperature or decreasing the temperature, it doesn't matter. It belongs to thermodynamics, right? Other branch of physics or other area or other topic of physics, topic of physics, excuse me, vibration and wave phenomena. I told you vibration, like this pendulum, vibration, right? Right now, the pendulum vibrates back and forth. This is vibration. Examples of, let's say, vibration and wave phenomena, a specific type, excuse me, this is the subject, specific types of repetitive motion, and examples like spring. This is spring. Actually, this spring is another example of vibration. Whenever you, for example, you stretch it, and after that you let it go. What happens to the spring? It vibrates, yeah? Right now, I stretch it and then I let it go. I release it. It vibrates up and down. A spring, pendulum. I showed you a pendulum. This is a pendulum, actually. This is a simple pendulum. It vibrates back and forth. And sound. Right now, I'm explaining the subject, so I use the vibration. Let's say, I make a sound by vibration, yeah, by vibration of, let's say, air particles. Air particles, let's say, about my mouth, actually, they vibrate, let's say, back and forth. That's why you can, let's say, hear the sound of your teacher or sound of your family member, any of your family member or anyone. So this is called, they belong to vibration and wave phenomena. Let's move on to another area. This area is called optics. I told you in the introduction of my, let's say, my lecture, I told you optics means anything that is related to our vision. This, they belong to optics. Optics, subject of optics like light, yeah, light. Examples of optics, mirrors, lenses, color, and astronomy. You know what mirror is, actually. Whenever you get, let's say, get out from your home, actually you check your image in a mirror. That's why you know what mirror is. Lenses, for example, this is the lens of my glasses. They belong to actually optics. Color, in general, color and astronomy. Astronomy talks about stars and planets in general and celestial phenomena. That's why they all belong to optics. Let's move on to another one, electromagnetism. the subject of electromagnetism, electricity, magnetism, and light. Electricity, magnetism, and they are subject. Let's read the example of electromagnetism. Electrical charge like electron, proton, they are electrical charges. Circuitry, let's say it's the collection of circuits. Electrical circuit, or whenever you wire your building, actually, this is called circuitry in general. Permanent magnet, like the magnet that we use it in a laboratory. They are called permanent magnets. And electromagnet, for example, any coil. This is a coil, for example. Imagine there's a coil, and by the way, this is a coil actually. Whenever the current passes through the coil, it let's say it can absorb or it can attract the iron. Automatically, whenever the current passes through the coil, it becomes a magnet. But it's not a permanent magnet, because whenever you cut the current, whenever you turn off the device, actually, that's why it returns to its original, let's say, original shape or original state. Actually, it returns to its original state, and it becomes a spring, right? Because so current causes the magnetism. That's why we say electromagnet. Without the current, this coil is just a coil. It's not magnet. That's why we say electromagnet. Let's move on to another one, relativity. Relativity theory, I told you. This theory was invented by Einstein, and I can say modern physics started from here. They are subjects of relativity theory, particles moving at any speed. Particles like electron, proton, neutron, subatomic particles move with a very high speed. This, let's say, phenomena belongs to relativity, including very high speed. This is the subject. About the example of relativity theory, I can say particle collisions. When two particles collide with one another. Actually, classical physics cannot, let's say, interpret it less accurately. Relativity theory can actually, by the way, I want to add something. Relativity theory right now has a lot of problems. I cannot say it's the perfect theory. It has a lot of deficiencies and problems. But for now, I say, of course, it's more modern than classical physics. Relativity theory. Particle accelerators. Particle accelerators, that they are, let's say, very huge devices. They mounted especially under the ground. They occupy the very wide area for example, for colliding the proton and neutron and electron together, and this is called particle accelerator. Particle accelerator is a device for colliding particles. Simply, we can say nuclear energy. Nuclear energy. You know what the equation of nuclear energy is. Let me write the equation for you. This equation is very famous for Einstein. Excuse me. We have an equation for nuclear energy is equal to mc squared. This is the equation of Einstein that, let's say, talks about the nuclear energy. Right? Another one, quantum mechanic. Quantum mechanic is the let's say, more modern than relativity theory. It talks about very small objects. After I explain this one, I want to, let's say, compare between relativity theory and quantum theory. But just right now, I want to read it. And after that, I want you to to be with me to compare between quantum theory and relativity theory. Actually, quantum mechanics, subject of quantum mechanics, like what? Like behavior of subatomic particles, right? Behaviors. How do they, for example, behave? Let's say particles. The example of subatomic particles, like the atom and its parts, actually. Quantum theory, let's say, could rearrange the atoms within the periodic table by, let's say, by means of their properties. Quantum theory can categorize the, let's say, the elements, can categorize the atoms in a periodic table. That's why, let's say, quantum mechanics is the last theory, actually, that I told you, that proposed by Max Planck on 1900. I want to compare between relativity theory and quantum theory. A lot of students say, teacher, what's the difference between relativity theory and quantum theory? Actually, relativity theory talks about very large object, very huge object, like planets, like stars. It doesn't have any speech about particles, actually. It's, of course, it cannot interpret the behaviors of particle exactly. It has some speeches about the particles, actually, like particle accelerator, but it's not accurate. Relativity theory is not perfect. But for getting more information about the particles or subatomic particles, we focus on quantum theory or quantum mechanics. Quantum mechanics is opposite to the relativity theory. Quantum mechanics talks about a very small object. It talks about subatomic particles and it causes, and actually, I told you, it rearranged the elements in periodic table, and it especially focuses on very small object. It doesn't have any speech about the large object. So in order to have a good theory, you can, let's say, unify quantum theory and relativity theory. This is actually, but together relativity theory and quantum theory can interpret some phenomena for us. Especially, I told you, for astronomy or large object, we focus on relativity theory. For very small object, we focus on quantum theory, right? They are areas of physics and their examples and their subjects. In your opinion, does physics have any, let's say, have any effect on manufacturing, for example, cars or not? Let's say, read this subject. So what are the areas that are used in manufacturing and making a car, for example? What are the areas? For example, electromagnetism, let's say battery, starter, and headlight. Battery of a car, or car battery, starter of a car, or headlights, they are, let's say, they are building, let's say, based on electromagnetism. Thermodynamic, let's say, is used in manufacturing car, like what? Like efficient engine and use of coolant. Like engine, actually. Engine, I told you, any motor, let's say, increases its temperature. That's why it belongs with thermodynamic. And we can say thermal motor, thermal engine. And coolant, radiator of the car. Let's say it cools down the car, actually. It lowers the temperature of the car. That's why they belong to thermodynamic. And I told you, anything related to changing temperature, it belongs to thermodynamic. We have another one, optics. Actually, optics is used in car, especially in what? Especially in headlights of a car, rear view mirrors, rear view mirrors and let's say headlights of a car are examples of optics. Vibrations and mechanical wave or wave phenomena are used in what? Vibrations are used in shock absorber. Shock absorber, you know what shock absorber is? Shock absorber is, they are springs, yeah? There are springs, let's say for each car, for each tire, there's a shock absorber, especially when the car moves above a, let's say, bumping, it vibrates back and, let's say, up and down, right? Radio speaker, radio of a car belongs to vibration and wave phenomena. And what do you say about the mechanic? Is mechanics, let's say, used in manufacturing car or not? Of course, because let's say the car moves, the car makes friction. Let's say, let's read the examples. Mechanics in a car, a spinning motion of the wheels. Actually, wheels or tires, let's say, have rotational motion. That's why they have motion. Any motion belongs to mechanic. It provides friction. Actually, there's a friction between the tire and the road. That's why friction, let's say, refers to the mechanic or classical mechanics. And that's it, right? I made this, let's say, information. I can say I turned this information into the question. It's the same thing, but I made it. I collected as a question. Number one, this is the first question actually. Each section of my pamphlet includes, let's say, a lot of questions. This is the first question. Name the topics of physics that are useful in building and operating a car. Actually, I explained it for you. Electromagnetism, thermodynamic, optics, vibration wave and wave phenomena, and the last one, mechanics. Let's say, explained it for you. That's why it doesn't need to, let's say, explain it again. Number two, the second question. How do designers use the principles of physics to design a sailboat? For example, you want to design a sailboat, right? Of course, without the knowledge of principles of physics, without information about the principle of physics, this designer, for example, cannot build any designer cannot build anything, right? And I told you, we are surrounded by physics in general. So what are the principles that the designer should focus on? This is the question. Answer. Designers try to what? Try to choose a convenient shape. So they concentrate on shape of the sailboat, and shape of the hull of the boat, and they concentrate on shape of the sail itself. They are, let's say, important, right? It says they try to choose a convenient shape for the boat's hull in order to what? In order to be stable, balanced, and floating in water, as well as, let's say, maneuverable, quick moving. Maybe you say, the teacher, what's the role of, for example, shape of the boat or hull of the boat hull, or what's the shape of the, for example, sail? Let me explain this one. For example, designers use in general, designers for example, sailboat. Why do designers, for example, use this shape? This is a trapezoid, actually. This shape is trapezoid. Why do they use, for example, this shape for manufacturing the boat? Why don't they use, for example, rectangular shape? Because it's not convenient, it doesn't work. But this one is maneuverable. It has aerodynamic. It can go through the water, and it can, let's say, make make room for itself. That's why it's, let's say, focusing on shape matters in manufacturing, especially boats. This is the hull of the let's say, boat, right? So it says they focus on the shape of the boat in order to what? In order to, let's say, in order for the boat to be what? To be balanced and floating in water without sinking. That's the first one. And I told you shape is very important, and maneuverable, quick moving. If you take a look at the, for example, this trapezoid. Let's say I told you the shape of the boat is trapezoid. Yeah, it's a trapeze. This trapeze is very sharp. You see, it has a very sharp, let's say, edges here. This sharp edges, let's say, enables the boat to go through, let's say, the, let's say, water, to penetrate through the water and make room for itself. So it has aerodynamic. That's why, let's say, designers of boats should concentrate on the mechanics, especially because whenever I say the shape is very important and the shape should be sharp, the shape should, let's say, should be sharp, and the hull of the, let's say, boat should penetrate through the water. For which purpose? The hull of the, let's say, boat should penetrate the water in order to move, actually. That's why I say, I said in order to move, so it belongs to mechanic in general. And this is another one, and it elaborates it. This is the answer, actually, which requires the knowledge of fluid mechanics, knowledge of mechanics of fluids, and motion and its causes, right? So the main goal for this purpose, the main goal for designing the boat is to actually, let's say, quick moving. Yeah, this is the main goal. That's all for today. I hope you enjoyed this lecture, and bye for now.